All right, guys, this is the E-Day number 2, question number 1 key. I'm going to work through this. If you would rather just scroll to the end of this video and you'll see the answers for A, B, C, and D, but I'm going to go ahead and work through it. A, determine the elastic energy stored in the compressed spring. So you have a spring, you have this figure here, and then we push C back. Remember, C is not touching, or is not connected physically to that platform, just resting against it. And so we want the energy stored, and this one's pretty straightforward. We're just going to use elastic potential energy. Formula is 1/2 kx squared. 1/2, the k is 400 newtons per meter. I'll give you that in the problem right there. And the distance it's compressed is 0.5 meters squared. And if you do that, you will get 50 joules. And I'm going to circle my answer. Then we're going to work down here, and it says block C is then released. So we're going to release it from this point. It's going to push to the right, and it's going to run into D, and then they're going to move off together. Remember, C is not attached here. They make that point down here. Remember that the spring is not attached to block C. But they want you to figure the speed of block C just before it collides with this block right here. To do this, we're going to do some energy conservation, and you're going to notice that, like I've taught you in class, I'm going to start with mechanical energy initial equals mechanical energy final. Well, we already found that it has 50 joules of initial energy. Now, we got to find the final energy, and there's two things that make up the final energy. One, it has kinetic final, but there's also some work from friction that we're going to add to that side as well, because they tell you that it has a surface and it has a coefficient of friction of 0.4. So we're going to go ahead and carry this on down. 50 joules equals, the formula for kinetic energy is 1/2 mass of block C, V squared, plus the work from friction is mu. They don't say whether it's static or kinetic. We're just going to leave it as mu, mass of C, times gravity, times that x distance that it slides. And of course, in this, we're looking for V. So we're going to come up here, and run out of room. So we're going to come up there and work, and we're going to go 50 joules. I'm going to subtract this whole thing, and so I'm going to go minus mu mc gx equals, and it has the kinetic after, 1/2 mv squared. We want to get the v by itself, so I'm going to divide through by an m and multiply by a 2, and that's going to give me v, and then do square root. And I'm going to skip a couple algebra steps here, but there's nothing that I think anybody can't handle. 2 times 50 joules minus 2 mu mg x, all right, all divided by the mass. Remember, this mu mgx is the work of friction. It's the force of friction, which is this. That's the force of friction times the displacement. That will give us the work, all right? And so now it's just a matter of plugging our numbers in. I'm running out of room a little bit here, but we're going to go ahead and see all the numbers plugged in. 2 times 50 minus 2. The mu is 0.4. They gave us that. The mass of that block is 4. G is 9.8. It slides 0.5 meters. And we divide by the mass of 4. And when you do that, you get an answer of 4.59 meters per second. I'm kind of out of room here, but that's what we're getting, 4.59 meters per second. And then we get to part C, the speed of blocks C and D just after they collide. So we're going to use momentum initial equals momentum final. We use conservation of momentum because these blocks are going to hit, and they do say they stick together. Right here they say stick together, and so they're going to move off together. And this becomes a pretty easy one. The mass of C times the velocity of C before, because it has momentum before the collision, is going to be equal to the mass of them together, because they're going to stick together, mass of C and D together, times the V prime. And we're looking for V prime, and so it's simply going to be MC VC all over MC plus MD. Put our numbers in. Mass of C is 4. The velocity, we're going to use this velocity that we found up there, and so we're going to plug 4.59 meters per second in, divided by the total mass, which is 6, 4 plus 2. And if you do this, you'll get 3.06 meters per second. So that's the answer to letter C. And then finally, they want to do part D, which is the horizontal distance the blocks move before coming to rest. They're going to slide off together, all right, and then slide and come to rest. Remember, the spring is no longer a factor here. So we're just going to use mechanical energy initial equals mechanical energy final. Initially, it has kinetic energy. They have kinetic energy. I'm going to use a capital M here, and that capital M is going to represent the mass of C plus the mass of D together, because they're together. And that's times V squared. And finally, the only energy that we have on this side of the formula is going to be the work due to friction, which is mu, the total mass, G times X. And again, that's the work due to friction. Okay, remind you, that's the force of kinetic friction times the distance they slide. We're going to take this formula, we're going to solve it for X, because that's what we're looking for. V squared over 2 mu G. And if you plug your numbers in, 3.06, we're using that right there, 3.06 meters per second, square that whole thing, divided by 2, divided by mu, divided by G, and you'll get an answer of 1.19 meters. And there you have it, all four of these. I'm going to put this in focus so you can see the answers. If you fast forwarded to this point, now you're going to see all four answers. 50 joules for A, 4.59 meters per second for B, C is 3.06 meters per second, and D is 1.19 meters. Please check out the second video, which will be the key to question number 2.